Consistent hashing is one of the most known algorithm in modern system design. It is that one algorithm that powers massive distributed systems like Amazon's DynamoDB, Cassandra, Netflix, and CDN providers like Akamai that serve contents across the globe. So in today's video, we are going to break down what is consistent hashing and why consistent hashing is needed and where do we use consistent hashing in real world system. But before we dive into consistent hashing, let's first understand the basic building block behind it, the hashing itself. Let's start with a simple question. If you have multiple servers, how do you decide where to store a particular piece of data? Let's imagine you are running an e-commerce website like Amazon and you have millions of users, right? And you want to store their sessions data in cache servers. One simple idea can be use a random function to assign each user to a server, but that leads to a uneven distribution of data. Some servers get overloaded and some servers get underutilized. So we need something more systematic. That's where hashing comes in. For example, let's say we have three servers. We can calculate hash of each user ID to give us a unique numeric value. Then again we can take a modulo 3 to decide which server should store it. This is because we have three servers and taking modulo 3 will give us a number between 0 to 2. This gives us a balanced and deterministic way to distribute the data. But there is a hidden problem here. What happens if one of our servers goes down or we add a new one to handle more load? Let's say we move from 3 servers to 4. Suddenly, our formula hash of user ID modulo 3 changes to hash of user ID modulo 4. This means almost every key now maps to a different server. All our cached data becomes invalid and our system will be facing lots of cache misses. And this is not good for scalability. So we need a smarter approach, something that allows servers to be added or removed without reshuffling the data. And that's where consistent hashing comes in. Consistent hashing solves this exact problem. Instead of directly mapping keys to servers using modulo operation, it places both keys and servers on a circular hash space, often called as hash ring. So basically earlier we used to take hash of user ID. Now we will be taking hash of user ID as well as hash of server IDs. And every user ID and server IDs will be mapped to different positions on the hash ring. Let's quickly see how this looks like. As you can see, we have a hash ring and we have three servers S0, S1 and S2 and 7 users named from user 1 to user 7. And in this hash ring, each user on the hash ring belongs to the server that is present in the clockwise direction from its position. Basically, if you can see, user 2, 3 and 5 are mapped to S0 and user 4 and 6 are mapped to S1 and user 1 and user 7 are mapped to S2. Now, when a new server is added, it only affects the keys between it and its previous neighbor on the ring. So instead of moving everything, only a small fraction of keys need to be reassigned. For example, in this scenario, user 3 and 5 are remapped to server 3 and other users are still mapped to their respective server as earlier. So this is the beauty of consistent hashing. It keeps our system consistent and stable even when nodes change. Now consistent hashing solved one big problem. It made our system stable when servers are added or removed. But there is still one issue, that is uneven load distribution. Let's quickly see what it is. Let's say you have three servers placed on randomly on the hash ring. If one of them happens to cover a large portion of the ring, it will end up with more keys and therefore more traffic, while another server might sit almost idle. That's not idle, right? As you can see, server 0 is having a bigger person in the hash ring, and any keys that is between server 2 and server 0, that will be mapped to S0. That means S0 will be overloaded with the traffic. And how do we solve it? To fix this, engineers came up with a simple but brilliant idea: virtual nodes. Instead of placing each physical server only once on the ring, we place it multiple times at different points. As you can see, we have two servers, S0 and S1. All the servers named as S00, S01, S02 and S03 belong to server 0, and S10, 11, 12 and 13 belongs to server 1. So uh, this makes the data spread out much more evenly. And when a server fails or a new one joins, the redistribution is smoother and better balanced. So to summarize, consistent hashing ensures minimal data movement when nodes change, and virtual nodes ensure balanced data distribution across all servers. And together they make the system both scalable and reliable. Now, you might be wondering, where is consistent hashing actually used? Almost every major distributed system uses it in some form. Let's look at a few famous examples. The concept of consistent hashing was first popularized by Amazon's Dynamo paper. Dynamo used it to distribute key value pairs across multiple storage nodes, allowing the system to scale horizontally while staying highly available. And another example is Apache Cassandra. It is a distributed database inspired by Dynamo, and it uses consistent hashing to partition data across nodes. Each node is responsible for a specific range of the hash ring, and virtual nodes ensure load balance. Even load balancers and CDNs like Akamai and Cloudflare use consistent hashing to route requests to the same edge server, which improves cache hits and reduces latency. So there you have it. Whenever you see nodes are being added or removed, and you want to minimize the redistribution of your data or your requests, you can use consistent hashing to solve that problem. And let me know if you want me to cover the mathematics behind the hashing next. And don't forget to like and subscribe for more system design stories.